In the previous unit, we tested hypotheses about proportions, and in this unit, we're going to test hypotheses about means. So first, remember that in order to use your data to make inferences about a population beyond the sample data, you first have to have a representative sample of the population for the question of interest. An example of that not happening is if you do a sample of only men, you can't generalize to women. That's just not going to work, at least usually. So hypotheses and conclusions are only going to apply to the larger population, which is represented by your sample. If the distribution of the variable is highly skewed, we should consider analyzing the median instead of the mean. And methods that do this are called non-parametric methods, but we're not going to get to them in this class. But one example of a situation where you do have skewed data is when you look at home prices. And if you look at home prices for lots of homes, there's a bulk of homes sort of in a modest range, and then there's lots of variability in the top end, and there are super expensive homes, like, out here is Prince's home, which is super, super fancy. So if you were to, say, make a bar graph of your data and it looks something like this, you probably should look at the median instead. And actually, if you ever hear something on the radio where they're talking about home prices, they do talk about the median. It's never the mean, it's always the median home price. So in this lesson, we're going to conduct significance or hypothesis tests with population means, and here are 3 situations you may be interested in. The first thing is hypotheses about one population mean. The proper symbol there for that population mean is this Greek letter mu. For example, we might want to determine if the mean body temperature is 98.6 degrees Fahrenheit. And in that case, our null hypothesis would be, well, that mean temperature is 98.6, and our alternative will be determined by the situation we're looking at. We could be looking at hypotheses about the population mean difference for paired data. Remember, you do this when there's some kind of natural pairing, and the symbol there is mu sub d. This is basically the same as mu, except for you collect your data, you find your differences, and then you average those differences. And one thing we might ask is the mean difference in height between college men and their fathers, is that 0? So that'd be like a null hypothesis of this mean difference equals 0. And we also could discuss the hypotheses about the difference between the means of 2 populations, and that would be mu1 minus mu2. This is when we have 2 separate groups. And for example, we might ask if the mean time of television watching per week is the same for men and for women. And the null hypothesis would be that things are the same. So that would be mu1 minus mu2 is equal to 0. That's the same thing as mu1 equals mu2. Now, the reason these tests are called significance tests is because the conclusion about whether to reject a null hypothesis based on a sample statistic is made if you're sort of significantly far from what we expect if the null hypothesis was true. That's why you're rejecting when you end up with big test statistics. Big test statistics are far from the mean and are unlikely if the null hypothesis is true. And we declare statistical significance and reject the null if there is a small probability that an observed difference or relationship in the sample would have occurred if the null hypothesis were true. So you have 2 things happening here. You have the test statistic, which corresponds to that p-value, and a big test statistic has a low probability. And I saw that in chi-squared values too. Big chi-squared was a low p-value. And the steps we're going to do for these tests are pretty much the same as the steps for the last chapter, just some of the details are a bit different. So the first thing is to figure out the null and alternative hypotheses. In this case, the null hypothesis defines a specific value for the population parameter. So your H naught should be a mu equals something, a mu d equals something, or a mu1 minus mu2 equals something. H naught should involve, and HA should both involve the symbol mu. You summarize your data into an appropriate test statistic. Now, just like when we did confidence intervals for means, where we use t-values, we also use t-values. You'll have to tell me that you're using a t-value. And the same format, it's sample statistic minus your null value. And in this case, you can't do, well, this standard error is a little bit different. So null standard error. So if we're looking at a population parameter that's a mean, the sample statistic for that is x bar minus your null value, which we'll just say is mu naught. And that null standard error would be sigma over root n, but you don't really know the actual true standard deviation, so this is s over root n, where s is equal to the sample standard deviation. All right, find the p-value comparing the test statistic to the possibilities expected if the null hypothesis were true. The p-value, how we're going to find them in this lesson, is using what's called table 8.3, which is in your book, or we're going to use software. There's also a table 8.3 in Blackboard linked with this lesson, so if you don't have one out, pause me now and print one so you can look at it, because it's a little bit trickier than the table of p-values for the z-table. So for step 4 and 5, like we discussed in the last stuff, basically are the same steps. Decide whether the result is statistically significant. That will be true if the p-value is small. And then report the conclusions in the context of the situation. You either reject or fail to reject the null hypothesis. You never actually prove H naught is true. It's just plausible. All right, just attacking some common misconceptions about hypothesis testing. One of the 2 possible conclusions in hypothesis testing is to accept the null hypothesis. I think I just said that this is false. You fail to reject H naught, but you don't prove it's true. You just don't know. The statement, reject the null hypothesis and accept the alternative, are equivalent. And this is true. If you reject H naught, you do so in favor of HA. For each of the following research questions, specify whether the population parameter is one population mean, the population mean of paired differences, or the difference between the means of 2 separate populations. So nutrition trends have changed over the years, and this may affect growth. Researchers want to know whether the mean height of 25-year-old women is the same as the mean height of 45-year-old women. And this is, so these 25-year-old women and 45-year-old women, they're not like mothers and daughters. There's no obvious pairing. Which means we have 2 populations. So let's say mu1 is equal to the average height of the 25-year-olds, and mu2 is equal to the average height of 45-year-olds. And what we're going to care about is mu1 minus mu2. And our null hypothesis will be that is this mu1 minus mu2 equal to 0? And that would mean that there is no difference in average heights in these populations. Versus HA, well, probably I would think if nutrition trends improved, we'd be alternatively thinking that the younger women were taller, which would mean that this difference is bigger than 0. So those would be the hypotheses that you're testing in this particular case. You plan to fly from New York to Chicago and have a choice of flights. You're able to find out how many minutes late each flight was for a random sample of 25 days over the past few years. You want to know whether one flight has a higher average delay. And this is sort of massively paired data. And the reason it's paired is that all data for one flight will be grouped together. Okay, now let's actually move on to doing some hypothesis tests with actual population means. So, what is normal body temperature? A paper published in JAMA presented evidence that normal body temperature is actually less than the conventional 98.6 degrees Fahrenheit. What would be the null and alternative hypotheses in this situation? So let's write them both in words and in symbols. And when you do them in symbols, you do have to use correct notation. Okay, so we're talking about a specific value, which means we're looking at a mean, not a proportion. So our null hypothesis of nothing going on would be that the mean body temp mu is 98.6. So the average body temperature is 98.6 degrees Fahrenheit. The alternative, which was presented in JAMA, is that the mean body temp is actually less than that. So that'd be mu is less than 98.6. Average body temp is lower than 98.6 degrees Fahrenheit. Suppose that in a sample of 16 adults under the age of 30, the mean body temperature was 98.2 degrees with a standard deviation of 0.497. Find the value of the t-statistic. So oftentimes I won't tell you that it's a t-statistic, so you'll have to tell me that you have a t-statistic by saying t equals blah. So make sure you state that. Now in this case, the formula is x bar minus mu naught over S over root n. And we're told that x bar, that's this 98.2. The fact that this is lower than 98.6, we're kind of saying like, well, is that lower enough to be actually different? Minus 98.6 divided by S over root n, which is 0.497 over root of 16 adults, so root of 16. Now you should be able to put this in a calculator in one go. If you put parentheses exactly where I put them, try to be more efficient with your work and put this into your calculator in one operation. You end up with a t-value of negative 3.22 if you do so. One problem with intermediary rounding is that this t-value might actually be off if you say, round this thing a lot. Next, we're going to find the p-value that corresponds to this t-statistic. So get out that table 8.3, and we'll talk about how to use that and how to use technology. So first of all, our p-value is the probability that we have a t-statistic that's more extreme than ours. So in this case, less than or equal to, because our null hypothesis has a less than, or alternative has a less than in it, negative 3.22. In a picture, the t-distribution looks a lot like the normal distribution. And we're saying if this is, say, negative 3.22, what's the probability that you're over there? Now remember, t-statistics have degrees of freedom. In this case, degrees of freedom is n minus 1, which is 16 minus 1. So the degrees of freedom here is 15. Okay, let's talk about how to do this in Excel first, and then we'll do the table. So in Excel, you type in t.dist, at least in my Excel, yours may be a little bit different. Type in the t value that you have, the degrees of freedom, and then this last thing, you just put in a 1, which means it finds all of that area. So we type in t.dist, we type in negative 3.22, 15 degrees of freedom, 1, which means it finds all the area, and this gives us 0.0029. So that's the exact p-value. And obviously on exams, you cannot use your computer, so you're going to have to use this table test to make the p-value, and in that case, I'll ask you for a p-value range. So p is still the same. It's the probability that we have a t-value less than or equal to negative 3.22. So on this table, look at the 15 degrees of freedom line. I'm doing the same thing right now. And across the top, you see that there are absolute values of t-statistics, and it says a p-value in the table is the area to the right of t. So when they have a t-statistic, say, of 3, which is the closest to what we have, they're looking at this picture and saying, okay, what's the area from that t equals 3 value over? Okay, now, so if we were to absolute value our test statistic, which was negative 3.22, we would get positive 3.22. Positive 3.22 would fall to the right of 3.0. And you can see what happens to the p-values as you go further to the right. At 2.58, it was 0.01. At 3.0, we're 0.004. So our p-value is going to be less than 0.004. And if you had your table, that's all you could say. P is less than 0.004. You should check, does that make sense with your p-value you calculated exactly? And the answer is yes, these do match, as in the second one makes sense with the first. So on your homework, I'm going to always ask you to do both. So this will be what I call a p-value range. Because on the exam, that's what you're going to have to do, is find the range of p-values. And then you can use the fact that you get the exact value with technology to check and see if your range is correct. Okay, using alpha equals 0.05 to determine whether or not you can reject the null hypothesis. Well, in this case, yes, because our p-value is less than 0.05. We can reject H naught, and we can accept HA. And in context, this will mean that the mean body temperature is less than 98.6 degrees Fahrenheit. Not every single person, but on average, the average body temperature is actually less than that. So that p-value stuff is sufficiently tricky. Let's actually find some find some p-values from tables and from software. So if we had the situation where our null hypothesis was mu equals mu naught, and HA was that mu is not equal to mu naught, given a specific n and a specific t value that we found. Note here the degrees of freedom would be 80. Okay, so what we will be looking for here, and because this is a two-tailed test, we're just going to have to do some doubling. The picture this is looking at is what's the chances your t is either bigger than 2 or your t is less than -2. So my value p is going to be either twice, 2 times the probability that t is bigger than or equal to 2, which is the same thing as 2 times the probability that t is less than or equal to -2. That second one is the one that you would actually enter into Excel. This is the direction stuff has to go. Excel always goes less than. So if you enter that, you'll have 2 times t dot dist, type in -2, 80, and 1, and you get 2 times 0.024, or a p equal to 0.048. This is also one that we can find in our table exactly. So same reasoning, p is twice the probability that t is bigger than or equal to 2. Go down to your degrees of freedom equals 80, and 2 is a number that's actually on your table. See that the p-value there is 0.024. So 2 times 0.024 is, once again, 0.048. So in that case, you didn't need to get a range. You can find it exactly from your table. All right, this one. H naught is that mu equals mu naught, and HA is that mu is greater than mu naught. So what we're looking for here is our p-value is the probability that we have a t that's bigger than or equal to -2. And the reason this goes bigger than or equal to is because of this HA's direction. You're always testing to see if your statistic is in the direction of that null hypothesis. And if you think about these curves, you say, well, here's -2, have the symmetric thing. I want the probability that I'm bigger than it. That means all this area, which is going to be a pretty big number. It'll be awfully close to 1. Okay, well, can you see that this is the same thing as 1 minus the probability that t is bigger than or equal to 2? So there would be 2, and this area over there is the probability that t is bigger than or equal to 2. So if I do 1 and take away that value, I'll get the probability. And this is 1 minus 0.024 from that table, which is 0.976. All right, suppose a study is done to test the null hypothesis H naught mu is 100, and a random sample of 50 observation results in an X bar of 102 and a sample standard deviation of 15. So first let's find the error, standard error. So what is the standard error of X bar? Well, this is S over root n. 15 over root 50 comes out to be 2.12 approximately. Then find the test statistic. So for t is equal to X bar minus mu naught over standard error of X bar. Well, our X bar was 102 minus mu naught, which was 100, over standard error of x bar, which I think I would prefer to put in as, once again, 15 over root 50. The unrounded one definitely is better. It'll be more accurate. And you get about 0.943. All right, on the basis of the information that you've been given, can the p-value for this test be found? If so, find it, and if not, explain what additional information would be needed. So first of all, we don't know HA, so we would need to know HA. In particular, is HA one or two-sided? And let's just, you wouldn't actually have to do this if this was a homework question, but just because that table requires, using it requires some finesse, let's just do some practice. So if it was the case that, say, HA was mu is bigger than 100, for example, then our p-value would be the probability that t is bigger than or equal to 0.943. So looking at a picture, that's to the right of 0, so bigger than 0.943, which is the same thing as the probability that t is less than or equal to negative 0.943. If you're going to compute this exactly, you have to do less than or equal to's because that is what Excel demands. So sorry, t.dist, negative 0.943, 49 degrees of freedom, and then 1, which does the whole area, and you get 0.175. And if HA had been that mu was not equal to 100, then your p-value would have been twice that number, or 0.35. But the point is you needed this. You need HA to do these calculations in the first place, so that's what's missing. A university is concerned that it is taking students too long to complete their requirements and graduate. The average time for all students is 4.6 years. The dean of the campus honors program claims that the students who participate in that program, their first year, have a lower mean time for graduation. There's no way to pull the records of all the students who have participated in that honors program, but a random sample of 25 students is taken, and the mean and standard deviation for the completion time for these students is 4.5 years and 0.5 years respectively. Carry out the 5 steps to test the hypothesis of interest, and we're going to use alpha equals 0.05. So first thing is the hypotheses. So H naught is that there is nothing going on, so the mean graduation time mu is 4.6. So the mean graduation time for students who participate in the honors program is 4.6 years. That would mean that nothing is different for this little set of students compared to the average students. And the claim of the dean of that program is that his students graduate faster, which means their means are less. Mu is less than 4.6. So the mean graduation time for students who participate in the honors program is less than 4.6. Okay, next next, let's compute that test statistic. So since we have means, the test statistic is a t-statistic. The formula we're using is x bar minus mu naught over the standard error of x bar, which is the same thing as x bar minus mu naught over s over root n. Okay, so for our sample, x bar was 4.5. The null value of the mean is 4.6, divided by s, which is 0.5, over root n, which is root 25. So this should come out to give you a t-value of exactly -1. So that tells you that in that program, definitely people do finish faster, but the question is, like, is this faster enough that is significant? Okay, find the p-value or give a p-value range. So first, let's note that the degrees of freedom here is 25 minus 1, or 24. So our p-value is the probability we observe a test statistic t that's less than or equal to -1. So looking at your little picture, you say, what's the chances I have something there or more extreme? So using Excel, this is t.dist, test statistic, 24, at least in mine you need that 1, and you come out to get a p-value of 0.163. You can think that these numbers are a bit like standard deviations. They're not quite like standard deviations, but they're pretty close. Once you get t-statistics in excess of 2 or -2, you pretty much get statistical significance, especially if your sample size is large. Okay, so that's the exact p-value from technology. Let's talk about how to use the table, just in case you're asked to use the table to estimate on an exam. Okay, so in the table, probability t is less than or equal to -1 will be the same as the probability t is bigger than or equal to 1. Excel goes to the left, the table goes to the right. It's really annoying, can't fix it, so sorry. Now, looking at your table for degrees of freedom equals 24, look across the top row, you have your t-statistics, 1.28, 1.5, 1.65. The closest one to 1 is 1.28. And your 1 is on the left of that. And notice that as you go from right to left, p goes up, right? If you look at the 1.65, that corresponds to a p-value of 0.056, 0.073, 0.106. So if your value is even more to the left, your p-value will be bigger than 0.106. That's all the information you could glean from that table, is that your p-value is bigger than this number, and that's good enough to draw a conclusion from. And is that true? Yes, 0.163 is bigger than 0.106. So either way, even if you only had the, p bigger than 0.106, that tells you that your p-value is not less than 0.05. So we note that p is bigger than 0.05, so you fail to reject H naught. And stating that in context, the proper way to say that is that there's insufficient evidence to conclude that H naught is true or H naught is false. And we'll write that in words. Insufficient evidence to conclude in this case that the graduation time is less than the average. So insufficient evidence to conclude that honor students graduate in a more timely manner than the general student body. Koala populations have been stressed in recent years by development and drought, and in the wild, koalas typically grow to weigh between 15 and 30 pounds. A random sample of 41 koalas was obtained, and each was carefully weighed. The sample mean was 20.75 pounds, and the sample standard deviation was 3.1 pounds. Researchers believe that the true mean weight of all koalas, if this is less than 23, then the population is suffering from malnutrition. So perform a hypothesis test to determine if this is actually the case. Okay, so first of all, this 23, that's your null value. One tricky thing is picking out that value from the problem. So your H naught will be that the true mean weight is 23 pounds, mu is 23. So true mean weight is 23 pounds. And HA is that, well, your mean weight is actually less than that 23 pounds. And I know I wrote 25. Let me fix that. That should say 23. And if you ever do statistics in real life, it might be as confusing as this. It's not going to be, no one's going to say, this is your null hypothesis, here, write this down. You're going to have to figure out what that is. And so here, what you're really trying to figure out is the mean weight lower than this? You kind of start with HA, and you say your null hypothesis is that your mean value is equal to that weight. So now let's find the test statistic. So remember, it's a t statistic is equal to x bar minus mu naught over the standard error of x bar, or x bar minus mu naught over s over root n. So our x bar was 20.75 minus 23 over s over root n, which is 3.1 over root 41. That comes out to be about negative 4.65. So the question now is this value low enough relative to that to conclude that malnutrition is actually happening? Okay, find the p-value or give a p-value range. So first note, the degrees of freedom is 41 minus 1, or 40. And the p-value is the probability that your t statistic is less than or equal to negative 4.65, which is in the correct direction for Excel. So this is t dot dist, negative 4.65, 40 and 1, and you get, well, my computer told me, first of all, was 1.793 capital E negative 0.5, and you're like, what the heck does that mean? That is not an acceptable answer. This is the same thing as 1.793 times 10 to the negative 5th, and that's like dividing by 10 5 times, and each division by 10 moves the decimal place 1 to the left. So that's 0.123401793. And let's just do at least 2 significant figures. So, you know, as long as you said 4 zeros, 18, I'm happy there. Okay, now from the table, well, your P is the probability that T is less than or equal to 4.65, which is the probability that your T is bigger than or equal to 4.65, same diff. So your table, degrees of freedom is 40. The largest t statistic you have is 3. 4.65 is to the right of 3, and as you go to the right, the p-values go down. So your p-value is going to be even lower, i.e. less, than 0.002. And is this true? Yeah, that number that we found with Excel was certainly less than 0.002. So state your conclusion in context. So we reject H naught, and we accept HA. And what HA is that the mean weight of koalas is less than 23 pounds. And is this evidence that the population is suffering from malnutrition? The answer is yes. Because if their weight is less than 23 pounds, then they are. So yes, this is evidence that the population of koalas is suffering from malnutrition. And the reason you can be pretty certain of that is you took a sample of, 41 koalas. You didn't just find the one fattest koala possible and say, no way, there's this fat guy, and therefore there's no malnutrition. You have to take a large sample and look at the average of that sample to draw these conclusions. Okay, that's it for the first lesson in chapter 13.